Okay, so hope you had a good weekend. Of course, this week is a short one. We've got class on Monday and we've got class on Wednesday, but then Thursday and Friday you've got February break. So that'll be a nice chance to decompress and catch up on things. Homework 4 is due on Wednesday, and remember that we went over some pretty detailed tips related to both of those problems at the beginning of class on Friday. So as you're working through problem 1, keep in mind that there's these kind of step-by-step suggestions on how to tackle that problem. And then I also offered some tips on the second problem as well. So if you want to go back and review the video for that as you're working on it, hopefully that'll be a useful resource. That needs to be submitted before class on Wednesday. I've got office hours this afternoon. And if you want to send me a message or stop by after my office hours, I'm always happy to help you if I'm available. I don't normally pre-announce quizzes. You know, we've got a handful of quizzes in this class, I think 3 through the semester, each of which is worth 1% of your course grade. So I'm not in the habit of routinely pre-announcing them. They're meant to be pop quizzes, but I do want to let you know that our first one will be on Wednesday. And in terms of coverage, it could be anything from the beginning of the semester up to and including the Hardy-Cross method, which we're talking about today. So please be sure to bring your laptop computer to class on Wednesday in case it's either a 3 reservoirs problem or if it's a Hardy-Cross problem. It would be good to be prepared. So does anybody have any announcement-related questions before we continue talking about the Hardy-Cross?
Yeah. Are you allowed to use pre-made files for Excel?
No. Anytime you're doing an assessment, like whether it's a quiz or an exam, I'm not so much interested in like whether you can adapt a pre-existing homework or template file that I've created. It would be you're starting from a blank workbook, and so you just need to start from scratch. Are there other questions? All right. So the first example that we worked with the Hardy-Cross method, I showed you the basic idea of how to determine flow balance. And that is that at each junction, the inflow and the outflow have to be equal, but it doesn't really matter what the distribution is, as long as at each junction it's satisfied. And so let me just reproduce this one that's on the screen right now, and let's just look at some different possibilities that would work. We've got flow coming out at the remaining 2. Okay. So in this one, there was 100 units of flow that came in at the bottom left junction, 30 that came out at the bottom right junction, 50, and 20. Okay. So the first thing we just want to basically look at is overall, is the inflow and the outflow equal for the network in its entirety? And the answer here is yes. So then it probably makes the most sense just to start at one of the corners that's the simplest. So by simple, what I mean is the fewest number of things going in and out at the junction. So at the top left and the bottom right, there's an outflow and also 3 pipes. So you could assign the distribution there and make it work, but it's just easier if you start where there's less going on. So either here where it's 50 or here where it's 100. So you just assume a direction, you assume an amount, and then everything else is going to have to like take those first assumptions into account. So we could say, for example, 5 and 95. Okay, so now if it's 95 going up, 20 going out, then that means I've got 75 left over that I have to assign between this pipe and that one. So let's say that it's this, and I've got 75, so it could be 50 and 20. Okay, now we're looking at this junction. If it's 20 in and 50 out, then that means that this has to be 30. And now let's just make sure that things work at this junction. They don't appear that they do. Have I done some math wrong? Oh yeah, here, 95 minus, so 75. I should have said 25. right? Because if I've got 95 minus 20 is 75, and so it would be 50 and 25. Okay, so then if it's 25 here, then it would be 25 there. Now I think it's probably going to work, where I've got 55 coming in and 55 going out. Okay, so just with that refresher, I've given you an example, a paper copy of the example for today's network. Let me pause for a moment, and I'd like each of you individually, without consulting with anybody else, do the same thing with this network. So use a pencil is my recommendation, and sketch on here the direction and the magnitude of the flows. So this is cubic meters per second. You don't have to necessarily write the units on the page, but just keep in mind that that's what it's going to be. And so let me pause for a moment, give you a chance to assess the network, assign the flows, and then we will reconnect in just a moment. And don't skip ahead and look at the flow rates that I gave you. Remember, there's a wide variety of options. There's not just one single answer here. It could be basically anything. All right, I was circulating around and it seemed like most people had the idea, and maybe the simplest approach is just to, with an inflow, in the absence of knowing other things, just splitting it 50-50. So you'll know here, for example, here at A, I said if it's 1 coming in, then I'll put half of it down through this pipe and half of it over through this one. But actually, I could make a better guess than that, because take a look at these two pipes. Pipe AB has a bigger diameter. Well, but it's longer. So longer is more resistance, bigger diameter is less resistance. So maybe I'll just leave it at 50-50. And then the same thing with this inflow. If 1.2 is coming in, I'll just split it 50-50 through pipe DF and DC. Although pipe DC in the end, it would be a shocker if it wasn't carrying more flow, because it's much larger and it's shorter. So let's just circle back to that at the end to see if, you know, if of the 1.2 coming in, I think it's preferentially going to face less resistance going through pipe DC than through DF. But in any ways, the main thing is that continuity has to be satisfied. Now, the rest of the procedure we're going to do, you'll never converge on a correct answer if you have any error here. The Hardy-Cross method is pretty good at correcting errors within the method, but errors in continuity, it cannot bounce back from that. So if you have any mistake in your network in terms of continuity, then you won't get the correct flow rates in the end. All right, so I just talked about, for example, how you split the inflows at A and D, and then if you know the flow through DF and the flow through AF, then EF has to be the sum of those two. And so if I've got 1.1 going towards E and 1.6 going out, then that forces me to have 0.5 going through CE. And if I had 0.6 going to C from D, then that leaves left over 0.1, and then that adds up to the 0.6, which is a known outflow at B. So this is my approach. You can use your flows when we go into the spreadsheet template, but that's what we're going to do now is we're going to take this initial flow balance and start translating it into the template file. And this is a little bit different from the template file that we used on Friday, because in Friday we had fixed R values, and now we're actually going to go full out, use the full version of the Darcy-Weisbach equation to model our friction losses, and we'll start off with the initial assumption of fully turbulent flow for F values, but then we'll switch over to the Jane equation after that. Okay, so let's go through this together. We're starting off with iteration 1, and you can see I've labeled loop 1 is the upper loop, and loop 2 is the lower loop. So let's start with loop 1. And which pipes are in loop 1? There's AB, there's BC, CE, EF, and AF. Now, is yours bolded automatically for CE and EF? I think it just, even though I deleted the previous answer, it retains the formatting. And the reason why that's bold is I want to draw special attention to the pipes that are common between loop 1 and loop 2. So if it's in both of the loops, we're going to do something special with those pipes. And so that's why it's bold, is to remind us that we need to get the most updated estimate of the flow rate, and it will come from the previous loop's calculation. So that's why CE and EF are bold. The other pipes in the network are only in loop 1. CE and EF, it's in loop 1 and in loop 2. So that's why it's bold. Okay, so here it said that all pipes have an equivalent sand roughness of 0.3 millimeters. So I'll say equals 0.3 divided by 1,000. Since here in the column header, it's defining the K sub S as meters. So 0.0003 for all of those pipes. Okay, now we'll put in the diameter. Pipe AB has a diameter of 0.5. BC has a diameter of 0.65. CE has a diameter of 0.6. EF has a diameter of 0.7. And AF has a diameter of 0.4. Now we need the cross-sectional area based on that diameter, so it's equals pi, parentheses open, parentheses closed, times the diameter to the power of 2 divided by 4. So the area is pi d squared divided by 4. Okay, and then we can drag that down to apply to all of the other pipes in the network. So we've got all of the diameters. Now let's just copy the lengths that are given. For pipe AB, that's 220 meters. For pipe BC, that's 100 meters. CE is 150. EF is 80. And AF is 180. All right. So the next thing is for us to estimate the F value. And we're assuming the fully turbulent flow assumption. And fully turbulent flow, here's the Jane equation. It says we've got a really big Reynolds number, so we're just going to use this first term in the logarithm function to estimate the F values. We're just going to use that for our first iteration because we don't know the flow rates yet. So F is equals 1.325 divided by parentheses ln of K sub S divided by 3.7 divided by diameter. I've told you before about this little shortcut of having it divide by something twice rather than using the parentheses for the denominator. So that this divided by 3.7 divided by d is the same as if I said K sub S divided by parentheses 3.7 times d close parentheses. Same thing. Okay, now I close parentheses for the logarithm, close parentheses for the denominator, and take it to the power of 2. We would just want to make sure that the F value is in kind of a reasonable to be expected range, and it is. The range of typical F values would be 0.008 to 0.038, and this is within that range. So this is just what it would be if the Reynolds number is so high that the F value only depends on the relative roughness. So it's better than just a pure guess of F value in the first iteration. It'll allow our solution to converge more quickly. And I applied that same formula down through the other rows. So does anybody have questions so far? Is there any step of this that I need to show again before we move on? Okay, now let's calculate the R value, and here's the equation for it. F times L divided by 2GA squared times D. All right, so equals F times L divided by 2 times 9.81 times A squared, so A to the power of 2, times D. So this is going to be the R value that is an overall, taking in all of the factors that account for flow resistance. And the higher the R value, the less Q we should expect to be going through that pipe to maintain the same amount of head loss through all routes in the network. So the R value for pipe AB would be 10.12. Now all of us should have these same answers so far. You know, we're going to have different Q value estimates because we all did our own thing for the flow balance, but these factors are not yet affected by any estimates in Q. Subsequent iterations, we may have slightly different values for F and for R, depending on what your starting assumption was for flow rates. But so far, there shouldn't be any divergence between what I've gotten and what you've gotten. What do we use for N? Well, that depends on our friction loss method. We're using Darcy-Weisbach, and so N is 2 at all points in the process. Okay, now we have to, when we put in the flow rates, we have to pay special attention to flow direction. And let me just do a quick screenshot here, and so I can paste it in for my network. So I'll paste this in and crop it. All right. So I'm going to put in my flow rates, assuming that clockwise is positive. And do you remember what we've talked about there? Where, so for example, AB is a flow rate of 0.5 cubic meters per second, and that's going in the clockwise direction within the loop. So when I put in the Q, I'm going to say 0.5 with positive 0.5, whereas BC, if you look at BC, that's against the clockwise direction, and so that's why I'd say negative 0.1. Okay, so put in your flow rates. I'm not going to narrate through because yours may be different flow rates than mine, but let's all put our initial guess flow rates in so far. And if you want, you can switch over to my numbers, or you can stick with yours. Either way is fine. Okay, once you've got the flow rates into the template, then this is where we start doing these calculations with R times Q and absolute value of Q, N times R times absolute value of Q. And this is, we're doing it because here is our formula that we'll do for the delta Q. This is kind of what the energy balance is built into this. It's kind of it's the heart of the method, is correcting for estimates of flow rate with making sure that the energy is balanced regardless of route. So R times Q times absolute value of Q. And we want to apply that for every row in the network. And then we need to add it up. underneath. And so that's sum of the cells above it. And then n times r times absolute value of q. And apply it to every pipe in the network, and then we can just drag this sideways because then that's going to add up the cells above it. Let me pause for a moment and circulate around in case anybody has questions so far. Okay, so once you've got this and that, the numerator and denominator, then we're going to calculate the delta Q for each row. And we're going to take the time to type this formula in over and over. We're not going to anchor the references because we want it to be a relative reference in subsequent iterations. So equals minus this one as the numerator divided by that as the denominator. And just repeat it for each row. Equals minus this divided by that. Equals minus this divided by that, and so on. Okay, so that's the delta Q, the correction factor. And then to find the corrected flow rate, it's your initial guess plus the delta Q. So it's the guess plus the delta Q will give you the new updated flow rate. Okay. Now these next couple of columns are going to be what we use to improve our guess for the F value in subsequent iterations. So we want to know the absolute velocity through the pipe. So that would be absolute flow rate, Q, divided by area. Q divided by A gives us the velocity, and if we just do the absolute value of the flow rate, then that'll give us a positive value for the velocity. And we need to know that because we're going to calculate the Reynolds number, and then that will be what we use starting in iteration 2 for our F value estimates. Reynolds number, remember, is velocity times diameter divided by kinematic viscosity. So it is equal to velocity times diameter divided by kinematic viscosity. I'm just going to type here 1e minus 6, and that means 10 to the minus 6th. And then I get the Reynolds number. All right. And then the last column, percent change, is just, it's not going to be involved in the calculations to adjust the flow rates, but I use it as a visual cue on whether the solution has converged. And so I want to know how much did the flow rate change from the initial input guess to the corrected guess, and assuming that the corrected is correct. So equals the corrected Q minus the initial Q divided by the corrected Q times 100. So it's like the updated guess of the flow rate minus the initial guess of the flow rate divided by the updated flow rate times 100. So that tells me, for example, that my corrected flow rate was 17% higher than my initial guess flow rate within that iteration. And my convergence criteria that I'm going to use is I want every pipe to be changing 1%. And this network is a little bit tricky because one of the pipes has so little flow that it's going to take us, I think, 4 iterations to get down under that percent change. So, all right. Any questions on the first loop of iteration 1? The second loop of iteration 1 is very similar, but there's going to be one little twist, and that's the common pipes. So let's say there's loop 2, and then we just want to start describing which pipes are in loop 2. There's pipe CD, and I don't know why I've got that one bold. Maybe because that's not one of the common pipes. Let me unbold that. There is CD, CE, which is a common pipe. There is EF and DF. So the two that are shared in common with loop 1 are CE, and that's bold already, and then EF. Let me bold that one. So that's just the designator that we have to pay special attention to the flow rates for those two pipes that are common. And the K values are the same, so let me just copy and paste the K value from the previous set. But we do want to put in the unique diameters for each pipe. So CD, it says, is 0.85 meters diameter. CE is 0.6 meter diameter. EF, 0.7. And DF is 0.5. And then the areas, I can just copy, because really what I want to copy is the formula. So if I just go to one of the previous areas and Control C and then Control V, it's going to paste the formula, but it's going to use the diameter for whatever row I'm on. So pi d squared divided by 4. So I can just copy and paste, and then it's going to update with the correct diameter to give me the correct cross-sectional area. All right, and let's put in the lengths here. CD is a length of 80. CE is 150. EF is 80. And DF is 200. Okay, F values are reliant on just the relative roughness, and so I don't have to type that formula in again. I can just copy and paste to get the formula that I want. So copy and paste. If we just look to make sure what it's referencing the K sub S and the D for the row that I'm in. So when I copy and paste, effectively what I've done is I've copied the formula to the row that I'm on. We can do the same thing with these R values, because the R values are just using only relative references. And so if I go up here into one of the R values, it doesn't matter which, just pick one, copy it, and then paste it where I want my new R value to be calculated. Then the R value it's going to calculate will be based on whatever row we're on. So R unique diameter, area, length, and F value. And then once it's there, I can continue the trend by dragging down. N remains as 2 for all of the pipes. Okay, now this is one of the times we have to pay special attention to the flow rates. And remember, now we're within the perspective of loop 2. So think about what's clockwise according to loop 2. So here was my initial flow guesses for loop 2. Okay, so pipe CD, that hasn't been changed. That estimate of 0.6, that hasn't been changed by the calculations that went on in the first loop. So the calculation so far didn't say anything about pipe CD. So I'm just going to say negative 0.6. And why negative? Because envision a clockwise direction within this loop 2. If the flow is going from D towards C, that's against clockwise. And so that's why I put in the negative 0.6. All right. What about the flow rate for CE? All right, now this is where it's bold and I have to pay special attention. CE, my original guess was that it was negative 0.5 cubic meters per second, but I've already updated that with a better guess of the flow rate because I have this corrected Q from loop 1. But loop 1 has a different perspective in terms of what's clockwise and what's counterclockwise. And so here I need to say equals minus of that corrected Q from the other pipe, loop. So it's the same magnitude, but just a different direction. That's what I'm using as my guess for the flow rate. Same issue applies to pipe EF, equals negative of the most recently calculated flow rate for EF, which is here. Okay, and then DF, I'm just using my original guess of 0.6. Because if you look here, pipe DF has not been affected by the loop 1 calculations that I did. So does anybody have questions about what or why we did here? Let me move that off to the side. Okay, so same thing here with the formulas. So I can just copy and paste without having to type it in again and drag that down through all of them. Copy and paste these. Now I want to add, so I want the sum of those. So equals sum, and highlight the cells above it that I'm adding. And then I can drag the sum function to the right. Let me pause for a second just in case anybody's got any questions. Okay, so now let's use the same formula for delta Q. It's equals minus of that divided by that. Forgetting the minus sign is one of the common mistakes that students sometimes make. So don't, it's hard not to see, it's easy to miss. But there is a minus sign there. Equals minus that divided by that. And then the corrected flow rate is the original guess plus the correction factor. Okay, so we've got corrected Q's. Let me do the same thing about calculating the velocities, just copied from the formulas that was above us. Same thing with the Reynolds number. I just copy and paste from the equations that I typed in before. And then even the percent change I can just copy and paste into this next loop. So some pretty significant changes, but this solution is going to converge pretty quickly. And that concludes iteration 1. Iteration 1 is finished. And so now we type iteration 2. And we can get all of this. This whole block of data is going to be the same for iteration 2. So let me just Control C to copy that whole block of data and paste it into the second iteration. Those are constants that aren't changing. Now F is going to change because now we're going to use the full version of the Jane equation for F. Rather than the fully turbulent flow assumption, we can do better now that we've got Reynolds numbers. So F is equals 1.325 divided by, parentheses, ln of K sub S divided by 3.7 divided by D. So that's the first term of the Jane equation, plus 5.74 divided by the Reynolds number to the 0.9. So the Reynolds number I'm going to use is this Reynolds number from over here. This is the previously calculated Reynolds number for pipe AB. So I'll say that to the power of 0.9 and close parentheses for the logarithm, close parentheses for the denominator, and square it. So it should look pretty similar to my previous F value, which was 0.0174. Now it's saying 0.0178. So it's a little bit different for that pipe. Some of the other pipes may be more significantly different. Just drag that down through all of them. And delete this one. So we've got updated F values for all of the pipes. Now, I'm not going to sweat the fact that EF doesn't have the same F value for each iteration. It will get there. It will converge without me having to, always use the most updated Reynolds number. Okay, but the R values. Okay, so all of these R values, I can just copy that whole, both loops, Control C, and then paste, Control V. So I've got new R values. Can take all of these N values, Control C, Control V, paste those. All right, now the flow rates. This is the last time we're going to have to really be meticulous about what goes into the cells. And from here on out, we're just going to copy and paste. So where's the best guess of AB? Equals here. This is my best guess of AB. And I'm not doing the minus sign because that's still the same loop, but just the previous iteration. Okay, BC equals here. Here's my best guess of BC for now. CE, I do have to put the minus and use it from within the other loop. So that's why it's bold. So equals minus. Here is my guess for CE, but I put the minus sign to flip the direction. Equals minus of here for EF. My best guess of AF is here. So once you've got the flow rates, then you can copy everything else for the entire iteration. All of these other calculations, Control C, but only for loop 1. And Control V. All right. So it's a good sign that my percent changes are getting smaller. That means that the iteration, that the solution is converging. Now I want to get the updated flow rates for the second loop of iteration 2. So what's my best guess of the flow rate for CD? It is this one. CE equals minus of this flow rate. EF equals minus of that one. And DF is here. Okay, now I can select all of this block for the remainder of loop 2. Control C and Control V to paste. Again, the percent change is getting much smaller compared to the previous iteration. The percent change was like between 20 and 40%. Now it's between 3 and 7%. So things are improving. I've only got 1 minute left, but that's all it's going to take, because now what I can do is I can just copy everything, Control C, Control V. Now this is iteration 3, and it's getting closer. There's just one pipe at this point because it has so little flow going through it, where the percent change is still above 1%. I can copy all of this and do another iteration, Control C, Control V, and this is my 4th iteration. And now I guess we could say that the flow rate is converged. This changed by 1.2%. Shoot, it's not too hard to do a 5th iteration if I want. I just go as many times as I like. But if you've got an error, then it doesn't matter how many iterations you're going to do, the solution will never converge. But here, the solution more or less converged after the 4th iteration. So what we'll do on Wednesday is we'll pick up here, so save the file, and we're going to calculate the pressures on Wednesday at the beginning of class. But this is the method that you can use to calculate the flow rates. Lots of places where, lots of opportunities for error. I really I like troubleshooting these spreadsheets, and so if you can't quite get yours to converge like this is, bring it by my office during office hours, and I'll help you find the mistake. I like I like going through spreadsheets. So I'd love for you to have a good working example to use as a basis for your homework assignment. All right, that's it for today. I'll see you in class on Wednesday. Remember, homework 4 is due before class on Wednesday.